Welcome to our next educational video with the topic Causes and Problems with Low Differential Temperature. After a short introduction, we will examine reasons for the low delta T syndrome and focus on optimizing hydronic circuits. After that, we'll explain how the delta T manager works and give a brief insight into the possibilities of digital monitoring. For years, people thought that HVAC systems were for comfort only. While we collected data to account for that comfort, we did not put much emphasis on collecting data to improve the efficiency of that comfort. As a result, we only looked at comfort when designing HVAC systems and rarely considered whether the same comfort could be achieved in a more efficient way. This focus on comfort has resulted in building designs that do not consider modern building technology. Even today we find modern, yet inefficient buildings. This is Chicago. Almost all the buildings you see are over 30 years old. Of course, some of them have been renovated in the meantime. But many have not. In fact, when buildings are partially renovated, they are often equipped with the same technology. Therefore, it is not surprising that the energy efficiency of these buildings does not improve after renovation. Imagine we were all still driving around in 20-year-old cars. When it comes to environmental impact, cooling and heating in commercial buildings is a major factor. In fact, heating and cooling account for about 40% of a building's energy consumption. In some buildings, it's even higher. Cooling buildings alone requires about 6% of the world's energy. The lifespan of a building is another important factor. While we can buy an electric car or replace its battery after 10 years, we want buildings to last for decades. Here, modern HVAC technology can help us improve efficiency and maintain comfort. The public awareness is changing. We are declaring climate emergency everywhere, banning gas boilers and combustion engines, but we quietly continue to build large commercial spaces with outdated HVAC systems because they are cheapest to install. More and more customers are willing to pay for efficiency. As we can see, there is a demand for energy-efficient buildings. This demand is doubling every 3 years. Therefore, the energy efficiency requirements for HVAC systems in buildings will increase significantly in the coming years. Low delta T syndrome is an often underestimated problem. But what exactly does it mean? The often too low differential temperature between supply and return in HVAC systems offers great potential for optimization. Many heating and cooling systems are operated with a much lower delta T than designed. Low delta T syndrome is caused by a variety of issues. Some of these are oversized pumps and valves, not ideal hydronic circuits, dirty heat exchangers, hydronic loops that do not have dynamic balancing. Although we can already see a high awareness of low delta T syndrome today, only little measures are taken to solve the problem. Let's briefly look at the optimization of hydronic circuits. Let's analyze the diverting circuit in a cooling application together. In full load operation, 100% of the water quantity flows through the consumer's heat exchanger and returns via the AAB port, the chiller. The system should now be operating within the designed parameters. In partial load operation, a considerable part of the cold water already flows via the BAB port to the return pipe. The delta T in the return pipe becomes significantly lower. In operating phases with low cooling demand, the delta T can reach 0. How can we now optimize the diverting circuit? The consumer circuit is variable flow and constant in temperature. The generator circuit is currently constant in volume. When choosing a new hydronic circuit, the consumer circuit should still be operated with variable flow and constant temperature. We achieve this mode of operation with the throttling circuit. Now the generator circuit has to supply the required amount of water for the current power demand only. The choice of hydronic circuit helps to increase the differential temperature in partial load operation. The question remains whether optimizing all hydronic circuits in an HVAC system is the sole solution? No. Unfortunately not. With optimized hydronic circuits, the easily recognizable problems are fixed. A great potential is found in optimizing the whole system. This is achieved by analyzing the flow and delta T of each consumer. Let's now recall the formula for thermal output. For a given constant thermal output, flow rating and delta T at heat exchanger are inversely proportional. If the volumetric flow increases, the delta T becomes smaller. On this slide we see the performance curve of a heat exchanger, measured with a Belimo energy valve. On the blue delta T curve we see how the delta T becomes smaller as the volumetric flow increases. Delta T decreases as the flow rating to power ratio decreases. What happens if the volumetric flow at the heat exchanger is higher than required? The heat exchanger is now operating in the saturation zone. The flow rating is higher than required, resulting in a reduced delta T without additional thermal output. In our practical example, the operating point 1 is 95 kW power output with a flow rating of 10.8 cubic meters per hour. At operating point 2, without delta T-manager, we achieve 98 kW current output with 13 cubic meters per hour. The heat exchanger is operated above the design point, which is called saturation. The power required to increase the flow can be calculated using the pump affinity law. The power for the circulation pump is proportional to the third power of the flow. Doubling the flow rating means 4 times the pressure loss and 8 times the current consumption. In our practical example, the increase in cooling capacity is around 3%, but the required pump capacity increases by 74%. In addition, the low delta T syndrome leads to higher costs for cooling. In poorly controlled systems, chillers often turn on and off, especially in cascades. Furthermore, the energy losses are increased due to the reduced return temperature. All in all, this leads to a significant increase in energy costs. The Belimo energy valve manages the delta T and, in combination with dynamic hydronic balancing, solves the low delta T syndrome. As mentioned earlier, HVAC systems have been equipped for years with thermal energy meters that collect valuable data on energy consumption. Often, energy statistics are done with a lot of effort. However, this useful data has only been used for billing purposes. While control valves provide some data to the building management system, they don't have the capacity to take thermal energy information into consideration. The Belimo energy valve connects the two worlds of field devices. It helps to optimize hydronic systems and increase energy efficiency. Seamless integration and cloud services open new possibilities for digital control and monitoring of HVAC systems. Let's take a look at the logic of the energy valve's delta T manager. The first step is to set the minimum delta T reference value. Now the delta T is set and we can open the valve and let it work as usual. If the delta T drops below the reference value into the saturation range, the energy valve will notice that. Now the delta T manager becomes active and reduces the overflow until the water spends enough time in the heat exchanger to release the required amount of energy. With the delta T manager active, the flow rate is automatically controlled to keep the delta T above the reference value and as close as possible to the set point required by the DDC. Delta T Manager Scaled is an advanced feature to account for changes in operating conditions. Compared to the previous slide where we explained the Delta T Manager, the Delta T Manager Scaled also takes the flow rate set point into consideration. This time, we set the delta T reference value and a flow rate for which this limit should apply. These are usually known values like the design parameters. With the delta T manager scaled, the valve will only enforce the given delta T at the given flow rate. Everything below this is scaled linearly to 0. When the flow rate changes, we can see that the delta T reference value adapts to the flow rate. In this way, the delta T manager prevents operation in saturation and optimizes the efficiency of your HVAC systems. A great feature that was added to the Belimo energy valve is the automatic creation of performance reports. It makes energy savings visible and ensures that you keep the efficiency of your HVAC system at the highest possible level. Inefficient operation, for example due to clogged heat exchangers, is detected and can be maintained accordingly. On this slide we see a practical example that illustrates the effects. The average delta T was raised from 3.4 to 6.7 Kelvin, reducing the chilled water flow by 49%. The annual savings add up to approximately $1.5 million. An increase in efficiency in the central heating and air conditioning systems can only be achieved if energy can be delivered efficiently and as required. In order to increase energy efficiency in buildings, modern HVAC systems with sophisticated field devices are needed. With this last slide, we have reached now the end of this learning video. We hope this presentation was educational for you. Thank you very much for your interest and attention.